Problem 6.108 or 7.104 for the given textbooks. For details, please see the description below. An air conditioner with refrigerant R34A as the working fluid is used to keep the room at 23 Celsius by rejecting the waste heat to the outdoor air at 34 Celsius. The room gains heat through the walls and the windows at the rate of 25 kilojoules per minute, while heat generated by the TV, the computer, and the lights amounts to 900 watts. The refrigerant enters the compressor at 400 kilopascals as a saturated vapor at a rate of 80 liters per minute and leaves at 1200 kilopascals and 70 Celsius. We need to determine the actual COP, the maximum COP, and the minimum value of the flow rate of the refrigerant for the compressor inlet for the same compressor inlet and exit conditions. We're going to start with a balance of energy for the compressor, assuming that there is no change in the potential and the kinetic energy. Then we simply write the rate of heat going in plus the amount of power going in plus the amount of energy that is carried by the system has to be equal to the rate of heat leaving plus the power produced and the rate of heat energy carried by the fluid. And then we simply see for the compressor there is no heat going in, there is no heat leaving, and we do not have any work produced. It actually requires power. Therefore, we simply say that the power going in is going to be equal to the mass flow rate and the difference between the enthalpies. Now what we need to find is the value of the enthalpies, and we also need the value of the specific volume at the entrance in order to determine the mass flow rate. So we go to the table, we go to table 812. For the inlet condition, we have a pressure of 400 kilopascals, and then we go across and we were told that it enters as a saturated vapor, so the amount of specific volume is 0.051266 meter cube per kilogram. And then if we go across once again to find the value of enthalpy, we find it to be 255.61 kilojoules per kilogram. For the exit conditions, it was given a pressure of 1200 kilopascals with a working temperature of 70 Celsius. We go once again to the table and we see that the saturated temperature is 46.29 and indicates that the working temperature is greater than the saturated temperature, which indicates that the fluid behaves as a superheated vapor. So we go to the superheated vapor tables for R134A, and we look for the pressure of 1200 kilopascal, which is 1.2 megapascals, and the working temperature is 70. And we see that the exit specific volume is equal to 0.019502, and the exit enthalpy is equal to 300.63. So this is a summary of the values that we obtain in the tables for the inlet and for the outlet. Now our next step is to be able to calculate the mass flow rate. The mass flow rate is simply going to be calculated by taking the volume flow rate that it was provided divided by the specific volume, and we're going to use the information at the entrance since that's the value that it was provided. So the volume flow rate is equal to 80 liters per minute, and the specific volume was given to be 0.05127 meter cubed per kilogram. We need to do a little bit of conversion in here. We have that 1 meter cubed is equal to 1000 liters, and we also have that 1 minute is equal to 60 seconds. So liter and liter cancels, and minutes cancel. Once we calculate this, we find that the value of the mass flow rate is equal to 0.0261 kilograms per second. Now we need to find that the amount of power that it goes into the compressor. We substitute all the values in here. We have 0.0261 kilograms per second, and the difference between enthalpies are going to be 300.63 minus 255.61. All of this is in kilojoules per kilograms. Kilograms and kilograms cancels. Kilojoules per second becomes watts. So this is going to be simply 1.171 kilowatts. The next step, we're going to evaluate the heat gained by the room, which must be equal to the amount of heat that is rejected by the air conditioning. That is simply Q dot L, which is the summation of what the heat that is gained through the walls plus what it is heated by the equipment. So this is the walls and the windows, what we're gonna have, the value that we have over here. That is equal to a rate of 250 kilojoules per minute. Once again, we transform this to be 1 minute is equal to 60 seconds. And we also add the amount that we have, the heat that is generated by the equipment, the computer, the TV, and the lights, which is equal to 900 watts. Make sure that we have to keep it in the same unit. So since this is kilojoules, it's going to be 0.9 kilowatts, just to be consistent. And then if we add these two values in the proper units, it will give us 5.067 kilowatts. Now what we need to do is calculate the actual coefficient of performance. So I'm just going to put A over here to be actual, and that is simply the ratio of Q dot L divided by the amount of power going in, which is the value that we calculated on the previous step. So we simply have 5.067 kilowatts, and the value we calculated previously, 1.171 kilowatts. It gives us that the actual coefficient of performance is equal to 4.33. Now, in order to calculate the maximum amount of coefficient of performance, we're going to do it based on the values of the temperature. So the coefficient of performance maximum is provided for a air conditioning to be T high minus T low minus 1. And then notice that T high is rejected at 34 Celsius, and T low, it is the temperature of the room, which is 23 Celsius. Remember, to calculate the coefficient of performance must be done using absolute units. So we have 1 divided by 34 plus 273. The low value is going to be 23 plus 273 minus 1. And we calculate this, and we see that the maximum coefficient of performance is 26.91. The next step is to evaluate the minimum volume flow rate. So we're gonna work our way backwards. We're gonna first find what is the minimum value of the power. So we're going to do in minimum. That is going to be found using the maximum coefficient of performance and the value of Q dot L, which is a fixed constraint in our problem. So we simply evaluate it as the value of Q dot L divided by the maximum coefficient of performance. So we have 5.067 kilowatts, and the maximum coefficient of performance is 26.91, and we find that the minimum power required is equal to 0.1883 kilowatts. Now that we have the amount of the minimum power, we're gonna go backwards and calculate the minimum mass flow rate. So this is going to be the minimum value that we're going to have, and that is going to be calculated simply by the minimum power that you have divided once again by the difference between the enthalpies. So HE minus HI, we take the values that we had from the previous part of the problems. So 0.1883 kilowatts, and this is going to be 300.63 minus 255.61. 55.61, and all of this is going to be kilojoules per kilogram, and this is going to give us 0.004182. And let's work on the units. Kilowatt is kilojoules per second, and this is kilojoules per kilogram. So notice kilojoules and kilojoules cancelled. This is kilograms per second, which are the units of mass flow rate. And then the last step, we find that the minimum value for the flow rate is going to be equal to the minimum value that we found for the mass flow rate times the specific volume. And all of this, once again, is going to be done at the entrance. So we take the values, 0.004182 kilograms per second, and we multiply by the specific volume that we found in the table, 0.05127 meter cubed per kilogram. Kilogram and kilogram cancels, and we find that this is equal to 0.002144 meter cubed per second, or if we convert it to the entrance units that they were given originally, this is equal to 12.9 liters per minute.